So we did a life cycle analysis, and what I'm going to show here are just some pictorial diagrams taken right out of the life cycle analysis. They're really probably a little bit too detailed for a presentation like this. So what you can do is you can focus on that red dot that's there, and that shows you the net electricity production, because there's some electricity saved in each scenario, and then there's some electricity generated in each or used in each scenario. So some saved, some generated, some used, and the life cycle analysis calculates what is net. What do we get at the end of the process out of this per ton of waste, or in total kilowatt hours per year. In this case, it's total. And you can see the one on the left is the large new waste-to-energy system, and that is no surprise. Waste-to-energy is designed to withdraw or extract the maximum amount of energy from the waste. The MBT, again, is no surprise that it has no net electricity generation, because it's not designed to do that. And the landfill scenario does have some, but landfill gas inherently has less energy, or the landfill system extracts less energy than a real waste-to-energy facility. Hot water generation, this is the district energy. This is what makes waste-to-energy actually very efficient, and it takes it from 27% efficiency to over 90% efficiency. And you can see that there's a lot of hot water in terms of the heat that is extracted from a waste-to-energy plant as compared to a landfill, where we also burn the landfill gas for power and extract the heat for district heating, but it's just not nearly as much. And of course, on the MBT, because we don't extract any energy, there's not much to be had. Petroleum consumption, no real surprises there. That yellow part of the bar, that's for transportation. That's the biggest part of it. At the landfill, of course, there's landfill equipment that also uses petroleum. And in this particular example, it assumes a backhaul to a remote landfill. If it were a direct haul, of course, that yellow bar would be about twice as high. Greenhouse gas emissions. We looked at this in the BC context, not a local context, but a BC context. And this is where the MBT has the best results, of course, because it's designed to reduce greenhouse gases. It's designed to reduce the activity of the waste when it's put into a landfill. So there's very little there. Keeping in mind this is for scenarios, so of course there is some coming out of it from the waste-to-energy that's already existing and will continue so. Landfilling and waste-to-energy are similar. Landfilling generates greenhouse gases from the methane that does escape through the liner system, and of course waste-to-energy generates greenhouse gases from the carbon or the fossil fuel-based portion of the waste, which is about 40%. In this particular case, based on our base model, the greenhouse gas from waste-to-energy is slightly less than from landfill. Mercury emissions. There are emissions from mercury in all of the scenarios. They differ somewhat. Waste-to-energy has slightly higher emissions. The good news here is that overall, compared to total emissions, they're very, very small in the region. And that black diamond you see there is actually the Canada-wide standard. If the facilities, all of the waste management facilities we build had to meet Canada-wide standards, the emissions would be like almost 10 times as high as they are now. And further, we will in BC be benefiting from a product stewardship program which pulls mercury-containing devices out of the waste stream. What doesn't go in can't come out. And I think that's a very progressive attitude we have here in BC. Dioxins and furans, it's the same thing. The Canada-wide standards are very high. The actual emissions are very, very low. In this particular case, it's reversed. The landfill has a little bit more than waste-to-energy. But again, overall, the contribution by these two dioxins are so low that they really have very little bearing on overall air quality. So what are the key lessons that we've learned from the life cycle analysis? And I have to tell you that there are other emissions of concern, but they will be talked about in the next presentation. Those are the common air contaminants. And they are different whether it's local or whether it's global emissions. And we focus primarily on the local emissions because that's what our airshed demands that we do. One of the things that we've learned, which surprises many people, is that transportation is not a key source of air emissions, including greenhouse gas. However, we did model the modern Trex, assuming that it would be in 2020, so we're looking at modern standards there. However, transportation is a major consumer of energy, so if you're shipping the waste a longer distance, it does make a difference. And of course, displacing natural gas through district heating avoids significant greenhouse gases and air emissions. And I see I'm running short on time here, so we did put together a financial model, and this has calculated the costs over 35 years, and we calculated them as realistically as possible. Of course, because we didn't do a design, there are some limitations there, but we used existing facilities to model them. However, please keep in mind, this does not include collection, this does not include transfer station costs, this does not include any recycling costs. This is strictly for the treatment and disposal of the residuals. And we also calculated some sensitivities, what happens if certain things happen. So these are the discounted system costs. This is what economists use. And we see here that the large new waste-to-energy plant has a slight advantage over long-distance landfilling, and MBT is by far the most expensive one. Perhaps the more telling graph here is the accounting cost one. This is where you see what the costs are going to be over time. If we depreciate waste-to-energy plants over 15 years, we can see in this blue line that sort of goes up in 2015 when we start constructing. It goes up again in around 2020 when we build a second stage. And then we depreciate over 15 years. And then when the capital costs are depreciated, we have revenues that offset any other operating expenses. And in fact, it goes down to basically a break-even proposition by 2037. The landfilling is that purple line, the dot dash line, and it continues to rise with inflation. There are some offsetting costs, but it's basically a steady increase. And the line at the top, the scary one where the costs keep increasing, that is NBT, and there's no surprise there either because there's very little revenue. There's a little bit of revenue from some recyclables, but it's relatively minor. But you have extensive costs of processing the waste. You have the cost of transporting it to a landfill. You have the cost of storing it into the landfill, and no revenue to offset it. And you have to continuously build more plants to handle the increasing waste volume. So that's essentially what the costs are about, and that's essentially a very brief summary of this report that we've worked on for a long time. Thank you very much.